All right, in this video lesson, we're going to look at the idea of what's called a function. So to start off with, all functions are related to a relation. A relation is just simply a set of inputs and outputs where all of our inputs are going to be paired with an output. Think of our inputs in any sort of relation as our x values, and think of our outputs as our y values. So for example, you might recognize a relation as maybe a ordered pair or a point of, let's say, 2, 4. 2, which is my x value, would also represent what's called my input, and 4 is my y value, which is my output. So a relation is just simply a set of inputs paired with an output. Now, what our goal for today is to understand if a relation is a function. So a relation is going to be a function if every input is paired with exactly one output. Okay? So take, for example, the number -2. Think of that as my input. When I take that input and plug it into, say, some function, what I should get is a single output out of this. What I do not want to see is I do not want to plug in an input, let's say, of -2 and see that I get potentially 2 or more outputs out of it. Say instead of -6, I might get a 4. So this right here, if I were to see 2 outputs, this would not be a function. So function means that for every input, there is exactly one output. So our first example, we're going to look at whether a relation is a function. So again, a relation is just going to be a set of inputs paired with outputs. So notice here we're given points. So in every point, you are given x's and y's. So all the numbers that come first, all of those are going to be my x's or my inputs, and all the numbers that come second would be my y's or my outputs. So what I want to know is this relation a function? And what I got to look for is to see whether each input is paired with exactly one output. So you'll notice here that -2 is going to be paired with 2. We see that -1 is paired with 2, 0 is paired with 2, 1 is paired with 0, and 2 is paired with 0. Now, in order for this to be a function, every input must be paired with one output. The way I like to look at this is that in terms of our inputs, and our inputs are simply going to be my x values. What I want, or what I guess I should say what I don't want, is I don't want to see any repeating inputs. So all my inputs must be different. So notice here I have -2, -1, 0, 1, and 2. So notice that I do not have any repeating inputs. Therefore, because I do not have any of that, this would represent a function. Now, you will recognize, hopefully, that while I do not have repeating inputs, I do have repeating outputs. So notice that, for example, I have -2, -1, and 0. All of those are paired with the same output of 2. That is okay in this case, because it is possible to have multiple inputs that have the same output. Think of, for example, in a car. If I'm driving a car and I want to come to a stop, I have a couple options. One, I can hit the brake pedal. The brake pedal will naturally bring the car to a stop. Now, that's not the only way I can bring a car to a stop. I also have an emergency or parking brake. So if I were to hit that lever or that button, again, the car is going to come to a stop. It's different from the brake pedal, but it does the same thing. I could also take the car using the shifter and put it in park. That would also lock the wheels and make the car come to a stop. So right there I would have 3 different things: a pedal, a lever, and a shifter that would all cause a car to have the same output of coming to a stop. So multiple inputs can have the same output, but we can't have one input having multiple outputs. Now, in the second example, again, set of points, what I want you to recognize here is that I have 4, 0 and 4, 3. So notice that I have the number 4, which is paired with both 0 and 3. So because I have an input that is paired with multiple outputs, this is not a function. All right, next example, we're going to view this in what's called a table, and then down here what's called a mapping diagram. And again, I'm going to look for do I have any repeating inputs? Remember, every input must be paired with a single output. So in this table, I'm given my inputs of -2 to 2 and my outputs of 3 all the way up to 8. So I want to know whether this relation is a function. So recognize in this table, in the middle, I see 0, 5 and 0, 6. That means the input 0 is paired with both 5 and 6. So would that represent a function? In this case, no, this would not be a function because, again, I have a single input that is paired with multiple outputs. And then lastly, my mapping diagram down here, I have the inputs -1 to 11 and my outputs of 4 and 15. So I want to know, is this a function? What you'll recognize here is that you'll see that, yes, I do have 3 and 11 that have the same output of 15. Use my analogy of a brake in a car. Multiple inputs having the same output is okay. So this technically would be a function. So again, looking at a relation and a function, we need every input to have exactly one output. Now looking at this, we talked about points, we talked about tables, that mapping diagram. So the last thing in order to view a relationship is through a graph. So I can take a relation, again, set of inputs and outputs, and I can plot those as points on a graph. I can plot those as discrete points, or I can form what's called a continuous graph, where you don't see discrete points, but instead you see a smooth line or a curve. So how do I determine if a relation is a function via a graph? What we're going to use is a useful little trick called the vertical line test. Vertical line, well, in general, a vertical line means a line that is straight up and down. Okay, so a vertical line would look like this, up to down. That's called vertical. So when I have a function represented on a graph, what I could do is the vertical line test is draw a vertical line through any or all points on my graph, whether the points, again, are discrete points or whether my graph is continuous. And again, in order to be a function, every input must have only one output. So if my vertical line passes through more than one point on my graph, then it is not a function. So represented here as discrete points. Notice that when I draw a vertical line shown in red here through this graph, notice that it hits 1 point. That means for this input of x, I would get a single output of y, that I would have an x paired with a single y. But when I go here, notice how it hits right there and right there. So I would have x paired with a y here, and I would have that same x paired with a second y. So let me call this y1 and y2. So that value of x would have 2 outputs, which cannot be the case. So whether the graph is discrete or continuous, our goal is to determine whether it is a relation or function. So again, this is called a discrete graph because we have discrete points drawn here. So what I want to do is I want to draw a vertical line through any set of inputs. So for example, if I draw a vertical line through that first point, notice it hits only once. But if I were to choose the input of 2, notice that it hits not once, but twice. Same thing if I draw it through not 2, but 5, it hits twice. So the inputs of 2 and 5 have 2 outputs of, for the value of 2 would be 2 and 5, and for the input of 5 would have 1 and 5. So notice those 2 inputs have more than one output. Whereas in this continuous graph shown here by a straight line, here if I were to draw a line through any input, say 1 or 2 or 3 or 4 or 5 or 6 or so on, and I can continue all the way through, notice how I only hit at 1 point every single time, which means that every input, say 2, is paired with an output 2. Every input 4 is paired with an output 3, and so on, that every input has exactly one output. All right, so whether we look at a relation or a function, what we're focusing on in any sort of function, I suppose, is the inputs versus the outputs, what we are plugging in versus what we are getting out. So all of the inputs, all the things that we are plugging in, that is called the domain. And all the things that we get out, that is called the range. Okay, so it's, again, we have our x values, which are inputs, our y values, which are our outputs. What we call those are domain and range. So to give you kind of an idea of a function, how this works, here's a coin machine. okay? Think if you have to do laundry, a coin machine, or you're going to an arcade. How this works is normally with a coin machine, you have your inputs. So your inputs would represent dollars, okay? And what you get out of that are coins, which are your outputs, okay? So what happens here is, let's say I plug in $1, I would get 4 quarters. If I plug in $2, I would get 8 quarters. If I plugged in $3, I would get 12 quarters. So these numbers of 1, 2, and 3, and so on, these would represent what are called my domain. The domain is just simply a list or a set of all the things I could potentially plug in, all right, versus my output, which is called my range. These are going to be the numbers that I could potentially get out of it, all right? Now, what we're going to think about is, what are the things I could plug in? Well, in a coin machine, I can only plug in whole dollars, all right? I can plug in 1, 2, 3, 4, 5. What I can't do in a coin machine is I can't plug in change to get change out of it. I can't plug in coins to get coins. What I can only do is plug in a whole number dollars. And what I'm going to get out of it are whole number of quarters. So depending on the type of function, my domain and my range might be discrete values, or it might be continuous values. To show you what I mean here, let's look at 2 graphs. So what I'm going to do in these graphs is I'm going to represent the domain and range. Notice in my first one I have what are called discrete points. Okay, so this is kind of jumping ahead, but this is called a discrete graph because I'm showing discrete points. Each of these points is represented by an input and output. So for example, I would have -3, -2. This would be at -1, 0. This would be at 1, 2. And last one, this would be at 3, 4. So in terms of my domain is just a list of all the x values. So I have discrete points, so I have -3, -1, 1, and 3. And my range, since they're discrete points, would be -2, 0, 2, and 4. Discrete points mean that I'm going to have discrete values for my domain and range. Now, a continuous graph is different because notice that I have only 2 points listed here. I have the value of -2, -1, and here 3, 2. But notice that I do not have discrete points in between, but instead I connect those 2 points, in this case with multiple lines, a line here, here, and here, so 3 different chunks. What this means is that when I connect points with a line or a curve, that not only do I want the values represented by the points, but I want all the values in between. So for example, my inputs, my domains go from -2 to 3. Because it's a smooth curve, what it means is I want every single value between -2 and 3. So not only the whole numbers of -2, -1, 0, 1, 2, and 3, but I also want all the fractions, all the decimals, anything in between. So the way we're going to write this anytime a graph is said to be continuous, we're going to write our domain and range a little bit differently. I'm going to start with my low value. My low value is -2. My high value is 3. In the middle, I'm going to put x, and I'm going to write this as what's called a compound inequality, that I want all the values between -2 and 3. So I'm going to use my less than symbols, but because we are using discrete points at the ends, meaning I want those points included, I'm going to use less than or equal to. So we're going to use a compound inequality to represent the domain. We would do the same thing for the range. My range, my low value is -1. My high value is 2. I'm going to use y instead of x because my range are all my outputs. And again, I'm going to use my inequality symbols of less than or equal to represent all the values between -2 and 3 for my domain and -1 and 2 for my range. All right, the last new term for this, so we have our inputs and outputs, which are x and y's. The list of all those are domain and range. So now once we get into real life applicable things, we're going to fit 2 new names to these, what's called the independent and dependent variable. So my inputs are always going to be represented what's called the independent variable. This is kind of a science-y term, but the independent variable is the thing that I choose, the thing that I'm going to plug in, the thing that I can affect. And the dependent variable is going to represent the output. The dependent depends on what we plug in. So for example, if I plug in $1 into a coin machine, That's independent because I'm choosing to plug that in. I can choose whatever I want. But the number of quarters depends on how many dollars I plug in. So the number of quarters I would get would be the dependent variable. So what we're going to look at is in a situation, what are independent and dependent variables, and then what would we get for our domain and range for these things. So let's say I have a function of negative 3x plus 12. So this is a function. Notice that within this, kind of written as a mathematical equation, notice you see the x and the y. So first of all, that x value represents my input, and the y value represents my output. This is called a function rule, where depending on what my input is, the function rule is going to tell me how I get my output. So what this means that when I have my x value, my input, I'm going to multiply that by negative 3 and add 12, and that should give me my output. Now what this function is going to represent is a real life situation here of the amount of fluid of juice you can drink in a bottle after you take a certain amount of gulps. So it says here that the number of gulps is x, and the amount of fluid left over, or the amount of juice left over, is y. So I want to know what is my independent and my dependent variables in this case. So we have the amount of juice and the number of gulps. So in this case, if we think through this, the number of gulps is going to represent the independent variable. Because I can take 1 gulp of juice, I can take 2 gulps of juice. I decide how many gulps of juice I'm going to take. But the limited or more number of gulps I take is going to depend on the amount of juice that's left over. So the amount of juice is going to be my dependent variable because it depends on the number of gulps. So therefore, if let's say I take 0 gulps, 1, 2, 3, or 4 gulps, what would be the amount of juice that's left over? So what this function rule does is for any given input, it will tell me what my output is. So my domain would be the list of all the number of gulps I could take, and the range is going to represent the amount of juice that's left over. So let's take, for example, I have an input of 0. I'm going to take that and plug it into my relation. So it says here negative 3 times 0 plus 12. And what that would do is that's going to give me a y value, in this case, equal to 12. So if I take no gulps, there's 12 ounces of juice left over. If I were to take 1 gulp, I'm going to do negative 3 times 1 plus 12. And what that would give me is 9 gulps. And I continue on. If I were to take 2, negative 3 times 2 plus 12, that means I would have, I would have 6 gulps left over. Now, one thing with functions that we're going to talk about is notice there's a pattern. So it's from 12 to 9 to 6. So as we do this, you can probably recognize the pattern, kind of guess what's going to happen next. But if I, again, were to plug in 3, negative 3 times 3 plus 12, that is going to tell me I'm going to have, in this case, 3 ounces of juice left over. And why I stopped at 4 is because if I take negative 3 times 4 plus 12, that means I would have 0 ounces of juice left over. So in the end, it would take 4 gulps to eliminate all the juice in that bottle. So in this, we looked at the idea of relations and functions. Relations, again, is a set of inputs and outputs. Function is whether there's a working relationship between them. We then looked at the idea of a domain and range as our set of inputs and outputs, and in a real-life situation, how that relates to the independent and dependent variable. So if you got any questions, make sure you jot those things down. Otherwise, we'll see you next time.